Welcome back, and now we're going to be going over spring and Hooke's law. Okay, so Hooke's law and spring. So, um, this is not intended to go over the details of how springs work and the derivation of Hooke's law. Instead, this is more of like a review to come up with a better understanding of what spring and Hooke's law is and how do you apply it in um, problems, or there are some scenarios where springs are being asked during the actual test. Now, here's a spring connected to a wall, okay, to a device, and the spring is laying horizontal. So I'm going to be going over some configuration of springs. Some of them will be installed horizontally along an axis, maybe inside a tube, inside a pipe. Um, some questions about springs hang from a horizontal plane, so it's hanging, so it's moving. So, or it might be on top of a horizontal plane where you have to apply a load on top of it. Okay, so different configurations, and at the same time, we will also go over um, compression and at the same time the extension spring. So compression is when you compress, like when you push the spring into a certain length, and then when you extend it, when you pull it, you stretch the spring. That's called what we call the extended spring. So let's go over it and analyze what is Hooke's law. So Hooke's law, according to Hooke's law, that the force of spring, so I'm not going to go over the derivation of Hooke's law, but instead, how can we use Hooke's law in terms of analyzing the amount of force the spring provides? So here we go. The force of spring is equivalent to negative K. Okay, so negative K multiplied by X. Now, that's the equation that's derived from Hooke's law, spring. Now, let me just add some information here where Fs is the spring force. So spring force, and that is measured in terms of newtons, where K is spring constant, and that is spring constant, that is in Newton per meter. Okay, so Newton per meter. And then X is the elongation or deflection, so elongation or compression. So when you compress, it's not appropriate to use elongation if you are actually compressing it. So the change in the length of spring, okay? So this is measured in terms of M. So by looking at it at what we call dimensional analysis, if F of S is in terms of newtons, and we have negative, and then you multiply it by Newton over M, and if your X is actually M, then it will cancel out. So N is equivalent to N. But there is this negative. Now, let us explain where the negative comes from. Okay, so let us explain where the negative comes from. And why is it it's negative? And later on, that equation, actually this negative will cancel out. It will just turn into positive. Okay, so allow me to explain it to everyone. So, first, we all know that this is a spring and there's no force. Okay, so this is your free spring. So free. So free spring. Nothing is influencing the spring yet. Okay, I'm not adding any force. I'm not applying any force on the spring. Okay, so what if I decide, again, what if I decide to apply force? Okay, so what if I apply to pull this? I will pull this, and what do you think will happen? Okay, so when I pull the spring, what will happen to this spring is it will elongate or will become longer. So let's say I pull this, 2, 3, 4, like this. So if you notice, it get elongated. Okay. So earlier it was this much. This is how long the spring is with respect to this wall where it's attached, or where the contraption is. Okay. And now we have this length over here. So now our spring is longer, okay, compared to its original length. And the force right here, in order for you to pull, then you have to exert force. Okay, so if you notice, every time you pull, okay, every time you apply a force, a spring force is always opposite. So the spring will always contradict your force, and it will be equivalent to the amount of force that you are pulling. So what does it mean? So if I'm pulling 5 newtons over here, the spring is also pulling it back 5 newtons. So that's your spring force. That's why it's always negative. Okay? So it's always negative because of the direction. So every time you apply a force, there's always a negative force, and that is the force of the spring. Now, and I mentioned earlier, it will be positive. Let's say that this is our L sub naught. Okay? And this is our L. You said L sub naught, or L sub naught and L. But we don't have L here. Instead, we only have X. Okay? So what do we mean by X? X, elongation or compression. So if I am going to extend this line right here and want to figure out the difference, okay, so the difference between the original length, so the original length and the final length, okay, so L is your final length, original length, and this change in delta or change in length is simply equivalent to our X in our equation. So this one over here is our X. Okay, so it means the difference. Okay, so difference. Now if I pull it to the right, the spring is negative because it's going to the left. Okay. Now how much force does the spring react? Okay, how much force does it provide us or go against the pull? It all depends on how far you change from its original displacement. Okay, so now let's apply the amount of force of spring. So we said earlier that F of S is negative K times X. And I mentioned earlier that it will not be that the negative will change into positive. Okay, so it will change to positive. Okay, so let's analyze this problem. What's the direction of force of spring? That is also the amount of force you are pulling. But since the spring is moving to the left, so the spring is pulling you to the left, this is negative Fs. We keep our negative right here. And then we have our spring constant. Now, what is our X? The final length minus L sub naught. Okay. But since we all know that L is greater than L sub naught, then our X is positive. Okay, X is positive. So all we can say is that this negative will cancel out. So we can just say that the amount of spring force is simply K L minus L naught. So this will prove that this is the magnitude. Okay, so the magnitude of Fs is K L minus L naught. Okay, so this is the first part. So spring, when you are pulling it, and what happened, you elongate the spring, causing it to react against the direction of your applied force. Now let us continue with the analysis. So this time, what I'm going to do is to apply force to the left. So instead of pulling this, I will be applying a pushing force. So I will push this to the left. So now I'm trying to compress the spring. And what will happen to the spring once you compress this? But before, we all know when we compress it, of course, the length will be shorter. So for example, now I have it like somewhere here. 1, 2, 3, 4. Okay. So it's still the same spring, but this time I compressed it. Okay. So I compressed this. So now I have a compression force. So now I do have a compression force F. Now where do you think is the direction of the spring force? So the spring force is always opposite. That's why it is negative according to Hooke's law over here. So negative means that the spring force is always going against the direction of the applied force. So if my length is about 3 units, so the amount of force should be the same as the force that you are, the magnitude of the spring force will be equal to the magnitude of the applied force that you are applying. Now, just like what we did on the other side, when we elongated the spring, when we pulled the spring, now we have the free length. Okay, so L sub naught is your free length. What I forgot to mention earlier, or let me just write it now, that L sub naught is the free length okay, so is the free length, and that is in terms of meters, and then L is the final length, that is also in terms of meters, and that final length, it's either compressed or elongated. And elongated is this example right here. So elongated, similar to this example right here. Now we have the second one. Now this one is being compressed. Now we have our final length of L. So if this is my final length, it's a little bit crooked, but I think that will help a bit. So now this is our X, which is the change in the length of the spring. So that's your X. Okay, so now let's apply the concept of Hooke's law. Let's see if we will still get the same result having positive and negative. So right here, I have the spring force Fs, which is negative K, which is spring constant, multiplied by the X. Now we have Fs, but our spring force is going to the right. And if it's going to the right, so it's not negative, but instead it's positive. So I will keep it as positive. Now I have negative over here. So now it doesn't make sense anymore because now it's negative and this one is positive. Oh, so there, what we're trying to prove here is not possible anymore, you might say. Now, how about let's try to figure out our x. Okay, x, which is our change in length, is simply our final length minus the initial length, L sub naught. But in our case right here, L sub naught is greater than L. So therefore, we can say that x is negative. Oh, okay. So now you're analyzing it, it's negative. So we have our fs over here, which is positive, negative, and this product right here is negative also. So k, which is negative. So what I'm going to do, I'm going to put negative, put the brackets over here, L sub naught. So this negative and negative cancels out because negative or not cancels, but negative times negative will give us a positive answer. So we can now be confident that the spring constant or the spring force is simply equivalent to K and L minus L naught, or we can just use it as X. So in the next videos, you will see some applications on different problems as I will show you in the succeeding videos.